So without further ado, let's get cracking. So you might be surprised to learn that drones go back in history quite far, such as this little guy, the British aerial target. And as its namesake states, it was an aerial target for the British Air Force. What's remarkable about this little aircraft is that it came only 14 years after Orville and Wilbur Wright actually made the first heavier-than-air flight, and less than 10 years after Shivka Bapuji Talpadi's first flight of an unmanned aerial test aircraft. So the Wright brothers made their first flight with a powered aircraft in 1903, and Talpadi demonstrated the first heavier-than-air flight with an unmanned vehicle in 1895. The other remarkable thing about this aircraft is that Heinrich Hertz only discovered the radio wave in the 1880s. And because of the rapid development in transmitters and receivers, this aircraft was actually allowed to come about. Pretty amazing stuff. Then we get into the world of machine learning, which is really cool stuff. It saves a lot of time. It can be done with RGB data, it can be done with multispectral data, it can be done with thermal data. What machine learning really is you have a map or a model and you train that model to look for certain elements in the environment or in that image, and then the algorithm will spit out the information you require. So in this example, a strawberry patch was scanned with an RGB drone. The machine learning algorithm was then trained. It was told to look for strawberries and also to give the strawberries various health values according to an RGB vegetation health index called the Modified Photochemical Reflectance Index. And then it was asked to show us where all the unhealthy plants were and where all the healthy plants were. And all of this was done through a seamless automated pipeline. So this allows us to train the model what to look for and then give us the tables of information very, very quickly to give us an overall look at each individual plant's health throughout the entire strawberry bed. And this is what it looked like. So it came up with all the detections and it gave us a health value, which we can now visualize by looking at these individual points that were created for each plant. So obviously the dark green points illustrate very healthy plants, whereas red points either unhealthy or dead plants, and kind of everything in between. And we can then see what some of this information looks like. It's also giving us the cover area or canopy area of each individual strawberry itself. These plant health values we'll get into in a bit more detail in the intermediate course, which follows the foundation course. Case, we'll use 40 meters. Brilliant. So now we understand what our ground sampling distance is, and now we need to have a look at what some of the photogrammetry requirements are. So if we're looking for a lot of three-dimensional information, our camera at a -75-degree angle is going to catch quite a lot of side information, which is really, really good. And that'll give us a better 3D model in the photogrammetry process. If we're doing a nadir mapping mission, which is a straight down mission, -90 degrees, where the camera is just looking straight down at the ground, which is probably the most common form of mapping mission flown. Our outputs won't have as much three-dimensional information, but depending on your image overlap or your mission requirements, this is a very effective way to map large areas. When we are looking at how the drone is actually going to fly in terms of its pattern when it's capturing the information, we need to consider whether we want more three-dimensional information or if we just need a good all-round orthomosaic and digital surface model, because this will obviously determine how many images are captured and what the photogrammetry software settings are going to be in terms of building the required outputs. Let's have a quick look at the object detection tool. So you can select whether you want to look for cars or athletic features or boats or planes. So let's say we're looking for these cars. We can run the model. If we just click detect, it'll take a few moments to run through. Brilliant. So once it has completed its task, you will see a little box materialize around the cars. It can make mistakes. This is a park bench, for example, so it has mistaken that for a car. But if we click on it, we can see the confidence that it thinks that it is a car. So it's quite low. It only thinks that it's about 43% right that it's a car. So you can run that through GIS if you export this shapefile or GeoPackage, whichever way you want to download it in. And you can then tell the GIS to rule out anything that is below a certain percentage. So you can give it a threshold and it will then know. So if we have a look at an actual car, we can see here that this is 93% certain that that is a car, and therefore it is correct. Fantastic piece of software, once more. It really is cool. If you're doing things like city planning and stuff like that, this is a very, very useful tool for counting the number of cars. In this entire map, it's detected 164 cars. This is quite a large map, so it's done quite well. Amazing. So here's a little bonus material as well for you. If you would like to add some different colors to these two different squares instead of having them the same color, we can add some different colors to those features by going back to our symbology. And instead of using single symbol, you can drop down and go to categorized. It'll bring up this window here, and under the value, you can either select the FID area or area in square centimeters or perimeter. Let's use the FID because this is simply 1 and 2, features 1 and 2. Once that's highlighted, you can click classify and it'll come up with some different colors for those features, which is very cool. This is an additional band which you can then remove. You just highlight that. All others, you can just click minus and that'll delete it. And by double clicking on the symbol here, you can then change the colors for those symbols. So we can make this one, say, a bright green. Okay. And our dark blue, we can then change to a brighter color. Let's say purple. And apply those two. So now you can see we've got different colors for our two different features. And we'll click OK. And you can see them come up in different colors there. You can then change the buffering color to match the feature color for that specific feature as well, to make it very clear that this measurement stands with this particular feature. Also a nice way to color your maps. Groovy movie. And then once again, as always, save, save, save again.